Yes. So I suppose I was a student of consciousness first and then became a clinical neurologist. And thanks, I'm a little tall. And only then started to dabble in the mathematics, which does mean that for this kind of audience, what I say is going to be hopelessly naive. And in particular, I'm interested in the geometry of perceptual space and time, and dare I say it, space-time, which will emerge from my talk. So I suddenly realized yesterday, for example, Sophia's talk, there's a great deal more sophistication in the room and online than I'm going to present to you. But I guess that's why I'm here, to learn something from you people. So let's march right on. This, by the way, was always going to be more the distortions of time and the geometry of time talk. The one I gave a couple of weeks ago in Stanford was the space talk, but because of Sophia's talk yesterday about manifolds and non-Euclidean spaces, I have managed to bring a little bit of the spatial stuff back in. So what am I going to do for you? How do I go forward here? Rory, is it just a space bar or something?
I think it's the arrow, or if you, yeah, apologies. I think the cursor just has to be brought back over here. Yeah, and then
there it's working.
you can click the arrows.
Okay, yeah. Great. So I'm going to be talking about motion, hence the title, and in particular, the experience of self-rotation, which is only a very specific form of motion perception, and how that might be influenced by spatial attention. I'm going to present a couple of experiments, not my experiments, but which I found fascinating, and give you the conventional interpretation, which I find paradoxical. I think I'm the only person that finds them paradoxical. But then I'm going to take the leap and give you a relativistic model of those same results, talking about the experience of self-rotation, constant velocity, but also angular acceleration. And then I'm going to tie it into something that I thought the computational science people in the audience might know a lot about, which would be the efficient coding hypothesis, and suggest there might be an efficient perception hypothesis. By the way, we've already heard quite a lot about that, but just in different terms. So, moving right in there. Oh, good, we can still see most of that experimental data. So this was a somewhat obscure experiment, but which really fascinated me. It's in a Japanese journal by Teramoto in 2004. Here, the experimental scenario is fairly simple. He's placed subjects in this optokinetic drum of a couple of 2.5 meters diameter. And this was typically, historically, what was done is you actually rotate the drum around the subject. Although in this particular experiment that was virtual, it was just what was projected on the drum and on the floor which was moving. And when that happens, most subjects experience something called vection, which is an illusory sense of movement. In this case, an illusory sense of rotation. So if your room is moving to the right, maybe for the first few seconds that it starts, you experience, oh, the room's moving, but very soon afterwards, you experience that, no, actually, I'm the one who's rotating in the opposite direction. What these guys explored, and I have no idea what made them think of exploring this, was, well, what about the perception of time while experiencing rotational vection? And they basically, you can kind of see it on the diagram there, they had a stimulus presented at 8 or 16 degrees to the right, and another stimulus presented 8 or 16 degrees to the left. Here I'm only showing you the data for the 16 degrees. So in other words, they've got two stimuli which are 32 degrees apart. And they basically just vary the objective stimulus onset asynchrony of those two stimuli, and then the subject has to nominate which one did they think came first. And you end up with a psychometric curve, which is at the top right. The one with the open squares is if the environment is not moving, and there's a very minor bias there. But interestingly, if the room is moving to the right, then the subjective simultaneity is distorted. And similarly, if you're moving to the left, but in the opposite way. And how you work that out is based on the psychometric curve. You can work out, when you extrapolate, what would be a point of subjective simultaneity. And with these particular parameters, with the stimuli 32 degrees apart, an angular velocity of 30 degrees per second, you find that this is, for example, with the environment moving to the right, vection to the left. What you then have to do is present the right-hand stimulus 24 milliseconds before the left for the subject to experience the two as being simultaneous. Now, just trying to get your head around that, what that means is that stimuli occurring in the part of the environment which is approaching you are temporarily promoted in your perception. So in other words, something on the other side, you have to present it earlier for the two things to seem like they are simultaneous. And by the way, I haven't shown you the 16 degree separation results, but it's pretty much half the degree. It seems to vary with the velocity of rotation. Pretty fascinating, right? Now, quite independently, another group presented another form of self-rotation perception and how it distorts the perception of time. So in this scenario, we've got a subject who they're actually sitting in complete darkness, which I'll show that on a white slide. But this person is on an accelerating chair, an angularly accelerating chair. They're similarly getting presented lights in front of them to the right or to the left. And midway through the ramp of their acceleration here, after 1.5 seconds at 36 degrees per second squared, the lights are shown with some sort of stimulus onset asynchrony, and they have to say which came first. And while I haven't shown you the results here, it's pretty much the same as in the vection case. Now, just let me point out to you that this is in complete darkness, right? So it's not as though the person is inferring self-rotation from the visual stimulus. Instead, what they must be doing is integrating a sense of angular rotation from the perceived angular acceleration. That's what the semicircular canals of the inner ear pick up. But basically, the effect is in exactly the same direction. So if you're being angularly accelerated to the left, then stimuli presented to the left seem to be temporarily promoted in your experience relative to stimuli presented to the right. But these other things I've shown you here are just some other really interesting aspects to the experiment. They didn't just do it with vision. They also did it with somatosensory stimulation. So that's what these little wires are showing you to each hand. So they also gave a little electrical sort of tap to both arms, and they asked people to do exactly the same determination of which came first, got the same result. And then even more fascinating, this is to remind me that they got the subjects to then swap the hands, okay? And it didn't, if for example, the subject is accelerating to the left, so that the left visual stimulus or the left arm somatosensory stimulus was promoted, then when they swapped the arms, the right hand but left-sided stimulus was promoted relative to the left. So concordant results. What the hell is going on? And this is what fascinated me. This stuff at the right, I'm only including that to remind me that I'm going to talk to you about this, which is the vestibulo-ocular reflex, but the point of them presenting this in the paper was they also tried giving the subject a marker to look at, which basically suppresses your vestibulo-ocular reflex. In other words, so your eyes don't move with your perceived rotation. It made no difference to the results. So, what is going on? So the conventional explanation, not that this has had a great deal of attention in the literature, is this what they call the prior entry hypothesis. And the idea is, oh, well, it must be because your environment is approaching, for example, from the left side. So therefore, it makes sense to attend to that region, and that that sort of covert orienting might mean that there's a reduced latency to representation of what's in that part of your environment. In other words, you represent it earlier than the stuff that on the other side seems to be, because it's going to be more salient, that's the part of the environment that's approaching. Seems sensible, but I don't agree with it. But anyway, what sort of evidence might we have for that? Well, there is a fair bit of evidence that you can distort time with attention. And the obvious one is in terms of choice reaction times, where you have to react to a number of possible stimuli. Interestingly, it's very much a sort of Shannon information theoretic relationship. So if you set it up so that a stimulus is going to be predicted, so it's got a very high probability, then someone's reaction time is reduced, and it follows the sort of Shannon surprise kind of relationship, presumably so that overall we get the best average reaction time over a whole lot of trials, or when we're experiencing the environment. By the way, Hyman discovered that within 5 years of Shannon's information theory being described, which I find interesting. It's if you look at how slow progress it is sometimes. Interestingly also, it does seem to, the probability or your attention to a stimulus does seem to affect perceptual duration by 40 milliseconds per bit. There's a whole lot of literature that supports that, by the way. It's not the subject of my talk today, but I've never got a good explanation from anyone as to why it's perceptual duration. In other words, a stimulus seems to last longer if you didn't expect that it was going to happen. Whereas reaction time it's basically how delayed your reaction is. So anyway, we can talk about that later. That's just to remind me, it's kind of like Morse code and information theory. But just specifically when we're talking about spatially oriented attention, I think one of the best examples is left hemispatial neglect. And this is the bit I've thrown in from after hearing Sophia talk yesterday. So I'll talk a little bit about that and how that might affect your perception of time, and then come back to that, the vestibulo-ocular reflex. So this is my clinical neurologist bit. I put my clinical neurologist hat on for a moment. This is what I see when I approach a patient with a non-dominant inferior parietal lesion, usually a right-sided non-dominant inferior parietal lesion, who are just looking and attending to the right side of their objective space. But hypothetically, they're actually turning their head and moving their eyes to what they consider to be the center of their space. Now, so that's just what it would look like from, if you're looking at somebody from the top, something like that, head and eyes looking to the right. And as neurologists, how we explore this is, just imagine this was a big sheet of paper I've given the subject, and I just say, right, mark for me where you think is the center of that line. And I think consistent with that idea that that their space is distorted, the person who's got this attention to this right side will not put the mark in the middle, but they'll put it over to the right side. By the way, in everything I'm going to show you from here on, the objective is always going to be in red, in other words, what we actually see, and the subjective is going to be in blue. Okay. So perhaps this isn't my idea, but this was someone else suggested this, perhaps what's going on is that the subject is putting the mark in the middle of what they consider to be their space. So in other words, perhaps their space is kind of curved like that, and perhaps, as you can imagine, if that was a curved piece of paper, maybe it really is in the middle of their space. And then you can map that onto what we actually record objectively. So the person who came up with that idea, although it had been, I think, suspected for a long time, was Biziak. And just to be somewhat provocative, I suppose, to tie this to my other interest in early 20th century physics, I guess you could possibly also call that length contraction to the right. Okay. Anyway, we can talk about that. Some people might even call it length dilation, but it depends on whether you're talking about from the objective to the subjective or from the subjective to the objective. Now, what's this got to do with time? I'm supposed to be talking about the distortion of time. Well, interestingly enough, the sort of temporal distortions are opposite to the spatial distortions. So that's an objective stimulus that lasts that length. If you get someone to look at that stimulus and judge how long they think it is, and we'll just assume that they get it right over in that side of their space. This is the part of their space they're really attending to. And then you present the same stimulus in the unattended part of their space. This is someone with hemispatial neglect, remember. Then they experience that stimulus as lasting much longer. So once again, this is someone who is looking and attending here to the right, who has a prolongation, a subjective prolongation of the stimulus to the left. That was Basso who described that more than 20 years ago. And just to be contentious, I'm going to call that time contraction to the left. Anyway, hopefully you're seeing this. This is in a qualitative way of describing it, but it's all kind of similar to the manifolds that Sophia was talking to us about yesterday. Now, I do need to just tell you something about the vestibulo-ocular reflex, because it's going to be vital to my explanation of what's going on. So you might have heard of this as the doll's eye reflex. So this person is looking straight at you. I apologize for my rudimentary animation in PowerPoint, but we'll see if it works. And then you imagine that you just wobble somebody's head slowly from one side to the other while they're looking at your nose. Oh, it's going incredibly slowly. That should be moving smoothly, but anyway, we'll accept that. But so you can. It's called the doll's eye reflex, because the idea is the eyes continue to look at what they're focusing on even as the subject moves. What I wanted to say about this is I'm going to tell you what the conventional explanation is of how this happens. This is something that occurs even in complete darkness. So the conventional explanation of this is that the subject perceives their self-rotation, or at least the rotation of their head, but that must be integrated just from the acceleration, because this occurs even in complete darkness, and then generates an equal and opposite angular velocity of eye movement to what they have perceived to be their rotation, so that the retinal image, if the lights were on, would be stabilized. Now, you can argue with any of these points, but I can tell you this is what every neurologist believes is going on. So we were talking more about with someone who's just subject to a constant angular acceleration. That was the Figliozzi experiment I showed you. And it's very much the same thing, except here that rather than having an alternating acceleration, you'd have a constant acceleration. So imagine here, once again, if somebody is being angularly accelerated to the left, of course they will experience self-rotation to the left, even in the dark. They will get a slow eye movement to the right. Interestingly enough, you also get a head turn to the right here. It looks something like this. Again, I'm going to have to, this is going to take way too long because it's so slow. But anyway, the bottom line here, what I'm trying to suggest is that the head turn that occurs when someone is subject to constant angular acceleration is in the opposite direction to the direction it should be according to that prior entry hypothesis. So remember that when you sense that you are moving to the left, you promote in experience temporally stimuli which are presented to your left. But at least in the case of angular acceleration, if you accelerate someone to the left, they get a left vestibular activation, which moves the head and the eyes to the right. In other words, you have to hypothesize that somebody is attending, if you're going to go with the conventional explanation, you have to hypothesize that somebody is attending to the opposite direction from their head and eye movement. And luckily I managed to keep talking during that very prolonged animation that was supposed to take 5 seconds. So that's what I just showed you about left vestibular stimulation. But you have to hypothesize, if you go for that prior entry hypothesis, that the attentional bias is opposite to the direction of head and eye movement. I don't buy it. So what's the alternative? I'm just showing you this picture to explain to you. I'm going to be just talking about your rotation. So I'm using the sort of aviation convention where it's going to be an angle of psi in the z direction. And so this is just a thought experiment, but imagine here Alice in the blue, okay, is sitting in the middle of an optokinetic drum, which is rotating clockwise at an objective angular velocity of rho, such that after some time she will have the drum will have rotated by rho tor, and then there might be some light that flashes on the screen, which would be an additional angle psi. Those are all objective quantities. Now imagine also there is an identical drum rotating at the identical angular velocity within which Bob in the red sits, except that he is angularly rotating with the drum. So in these two scenarios, Alice will experience vection anti-clockwise, some people would say counterclockwise, whereas Bob, even though he's rotating, will get this illusory sense of being stationary. How would we represent Alice's experience relative to Bob, or Bob's experience relative to Alice? Now, how you might think is something like this. So let me just explain this. These are going to become something like space-time diagrams. See, the thing which is slightly strange here is time is progressing upwards on the screen, okay, whereas angle, the angle of yaw is on the horizontal axis. Now, remember, Alice was in blue and Bob was in red, and Bob basically is rotating with the drum. So you can think of the red angle and time parameters as being objective angle and time parameters. You might think it would be something like this, where the slope of Bob's angular coordinates relative, when embedded in Alice's, which is A here, would be just rho. You think that's fair enough, but then you might also imagine that you could embed Alice's spatiotemporal experience in the coordinates of Bob on the left here, and it would be sort of symmetric in the opposite direction. I think this would be what most people would say would be reasonable. You'd be able to come up with a sort of mathematics for that transformation, and you would say, well, here Alice's yaw and time is in the Latin alphabet, whereas the objective is in the Greek, and you'd say, well, we have a relationship. But clearly, this must be wrong, right? Because this would suggest that the simultaneity for Bob would be exactly the same as the simultaneity for Alice, whereas the experiments I've shown you just are not consistent with that. So I've only shown you this to show you what must be wrong in what seems like an obvious explanation. And now I'm going to dive in to something which I hope you find challenging. That's wrong. But what about this? So, busy slide, I'm sorry, but this is a very similar idea where in A, on your left, Bob's coordinates, which are the objective coordinates, are embedded in Alice's coordinates, and on the right you imagine Alice's experience of space and time being embedded in Bob's objective coordinates. Now, just to explain some terms here, I've now separated omega here, which is perceived angular velocity, from actual angular velocity rho. And I'll start by telling you about omega. The idea here is that not only do you have that gradient relative to this axis, but also the simultaneity axis. In other words, constant times are similarly distorted. The other thing I'd have to point out here is that I've changed coordinates in a weird way, so that time is now in radians. What's going on there? Well, this whole coordinate transformation, which is a Lorentz transformation, ensures that omega here cannot exceed a value above that green line, which is a sort of maximum, a boundary to perceived angular velocity of rotation. Now, you'll probably already have realized this is very much special relativity, except I've just borrowed the mathematics in that we're talking about something very different here. We're talking about perceived angles. But by assuming that maximum perceived angular velocity is 1, what I have to do is I have to alter the units, in this case of time. If you think that's just really wrong, that's exactly what physicists do, except they alter the units of distance and talk about light seconds or light years, and then seconds, in order that they get to the speed of light being 1. So I've done the same thing, but I've altered the time units. And similarly on the right, now you'll notice that if you do this transformation, that these diagonals, they diagonalize both coordinate systems, or indeed any coordinate system of someone who's got any form of constant angular velocity. That's, by the way, a form of symmetry, like once again Sophia was talking about yesterday. So I'm calling gamma that maximum perceived angular velocity. We now have completely different transformations, but where, as I was saying, the two concepts of time are different. And we have this factor beta that comes in there, which in special relativity is called the dilation factor. And now I was going to tell you about the objective angular velocity. I've written there rho. That's actually, in relativity, would be called the rapidity. So, in other words, there is a relationship between objective angular velocity, which is additive here, and subjective omega, which is the hyperbolic tangent relationship. And so you can think of rho in this diagram as being a hyperbolic angle there, which varies from 0 to infinity as omega varies from 0 to 1. Phew. I've thrown a lot at you in that slide, and I apologize. But really, if you want to think about it some more, it's basically I've put all of Einstein's special relativity paper in that one slide. So getting back to the vestibulocular reflex, why don't I just remind you of this again? Well, you can even then. What I was going to mention about this is, remember how we were saying that the central hypothesis is that with the vestibulocular reflex, the eyes move exactly to compensate for perceived angular velocity. What that means, can I not go? Have I moved this thing? Seem to not be able to. Oh, there we go. So here we just look at the data set. First, this is a historical data set of people who are being angularly accelerated on block at 100 meters per second squared. And in fact, the compensatory eye movements, the vestibulo-ocular reflex, doesn't entirely perfectly compensate for the objective angular velocity of rotation. It starts to, but once you get to higher velocities, it asymptotes. And interestingly enough, if you work out, well, perhaps this asymptotes at around about 200 degrees per second, if you then assume that you've got a relationship which follows from what I just told you about the vestibulo-ocular reflex of the eye movements compensating for perceived angular velocity, and if you then put in the figures that I showed you for Teramoto's experiment in terms of the angular velocity, and here t being the point of simultaneity, so t is 0, you get exactly the latency distortion that was actually recorded. I'm probably just about out of time, so I'll finish up. So does that also apply here? Well, this is what, just say instead of Alice having this percept of constant angular rotation, what if instead Alice is being angularly accelerated to the left? Okay, so from what I showed you before, you might expect this from here to here. She's at first moving infinitely fast to the right, perceiving a maximum angular velocity to the right. But then basically she has this acceleration, so eventually she's perceiving a maximal angular velocity to the left. But this is also a subjective space-time, I would contend, so that you should also be able to diagonalize all of her coordinates. Again, this is something just lifted out of special relativity. These are called the Rindler coordinates. And you look just at the bit which is of relevance, perhaps from what Alice considers to be pi(2) to the left to pi(2) to the right, and you take what would be the objective midpoint, you would find that Alice is actually will pick a point to the right of the midline, even when accelerating to the left. So in other words, what I'm showing to you there, it's, by the way, it looks also, that's the maths of that equation. It looks very much like left vestibular stimulation. So the efficient coding hypothesis, I don't think I'm going to go into this in any detail because you guys know it, I think. The idea here is that if you have no noise between stimulus and response, so that the conditional entropy of the response given the stimulus is 0, then you can maximize what the response tells you about the stimulus by maximizing the entropy of the response. So people have been talking, I don't know if you all knew this, people use these words like entropy maximization, histogram equalization, they're talking about this. But this is pretty much, at least in neuroscience, usually applied to neural coding, firing rates, for example. So, this is my final slide. So, how might we apply this to perception? So here, I'm showing you perceived angular velocity only between these two limits. I've gone back to using degrees again, so 200 degrees per second plus or minus, okay? So we imagine it's finite between those boundaries. Bottom right, I show you objective angular velocity, right, okay? And this in between is that same transformation I showed you before. It might look very different, but that's because here we're taking both plus and minus. I only showed you that part of the curve before. So what might be going on? Well, hypothetically, there may be an objective distribution of angular velocities to which we are exposed in a lifetime of just naturalistic immersion in the environment, for which this transfer function would be the cumulative. What does that mean? Well, mathematically that means that it would transform this distribution of objective angular velocities into a completely flat distribution of perceived angular velocities between those limits. Now, is this the distribution of objective angular velocities to which my body is subject in a lifetime of experience? I don't know, but I do know that the work has already been done on monkeys climbing in trees, where they basically look at this very question. Unfortunately, they've just been looking at head rotation, not at body, which makes a big difference. So we don't know, but it's a potential test of the scheme. So, I think I've just said that. For some reason I don't seem to... Oh, here we go, discussion. So these are just things that you may wish to ask me about. So I've talked about angular velocity, but of course maybe there's also such things as linear vection. Could that be extended there? Finite perceptual variables, generally there's lots of others. Your perception of depth, for example, when you look up at the Greek sky tonight, you will see a celestial sphere, even though objective distances of those stars vary greatly. But again, we've got a finite perceptual variable. I'll just go back. Even though we've got a potentially infinite objective variable, could we apply something similar? You might have noticed, this was the bit I threw in last night and I've gone over my time, I'm sorry, that there seems to be here this, I'm going to call it a neurologic equivalence principle. Again, I'm being provocative, between the experience of angular acceleration and the experience of attention, at least spatially focused attention. Now that's got to be interesting, right? Because that was, Einstein's great idea when it came to objective physics. And so this is hoping to inspire you people who know more maths than me. Can we extend all of this to some sort of general relativity of perception, perhaps where attention, at least spatially focused attention, might take the place of gravity, and where information might take the place of mass? Maybe next Neuromonster talk. Okay, I'll leave it there. Thank you very much.